Hello BNG426 526 class. This is the pre-lecture for Wednesday's flipped classroom activity, where we'll be talking about mass balances. We'll be talking about the black box, and we'll be talking about aromatic amino acids. So, we talked about this past week, we talked about stoichiometric calculations for cell growth and how to use them to figure out our material balances. So we know our compositions of our substrates typically, if we're growing cells on glucose. Well, we know how many carbons, hydrogens, and oxygens are present in glucose, and we typically will know the composition of our products. You know, the main ones being carbon dioxide, water as well as whatever our main value-added product is. So for Saccharomyces cerevisiae, when we're thinking about ethanol, then we know the chemical formula for that for sure. The composition of cellular material might be a little more involved, but a lot of formulae for cellular material have already been established under different conditions. And you saw in the book that there is a whole table that lists a bunch of those. So, you know, even if we are working with something that's not in that table, we have a general idea because there is a general formula for cellular material, and we could just, as a default, we could just use that. So because of that, we can write material balances. We can write material balances for cell growth and cell growth with production. And of course, as is the law of thermodynamics here, mass in is going to equal mass out. Okay, so again, we'll go back to the chemical formula for cellular composition. So 1 mole of biological material is defined as the amount containing 1 gram of a carbon atom, and the formula, the general formula, is written like this: CH to the alpha, O beta, and delta, where alpha, beta, and delta are certain numbers, and those numbers aren't necessarily integers. And we will abide by this general formula for Wednesday's exercise. So again, we're just focusing on the elements carbon, hydrogen, oxygen, and nitrogen here. And again, the organism of choice for Wednesday, which is E. coli, the book has specific formulae for that organism. We can, even if we're not doing the exact same conditions as specified in that table in the book, we can just choose a formula, an E. coli formula, irrespective of whatever conditions may be specified. Okay, so again, you know, we went through the whole growth and production as a chemical reaction or as a chemical equation formula here, where we had carbohydrate as our substrate. We typically kind of normalized it to 1 mole of whatever carbohydrate we were looking at, typically glucose, could be something else though. In the homework that was just assigned, it's ethanol as the substrate. But we have with 1 mole of carbohydrate, we would use A moles of oxygen, B moles of ammonia to give us C moles of biomass, D moles of water, and E moles of carbon dioxide. And of course, that changes a little bit if we add production into the mix. We would have yet another chemical formula on the right side of the equation here. We could put together our elemental balances and kind of go from there and begin to figure out exactly how much of everything we need in order to get growth in this case. So we can put our carbon balance together. We can look for everything that has carbon, and we can keep the reactants on one side of the equal sign and products on the other side. We can do the same for hydrogen, oxygen, and nitrogen, where we are taking into account, for example, hydrogen, we're taking into account this m moles of hydrogen per mole of carbohydrate plus 3 moles of hydrogen and ammonia multiplied by how B moles, we need B ammonia per 1 mole of carbohydrate. On the other side, on the product side, we have alpha moles of hydrogen in the biomass multiplied by C moles of biomass per mole of carbohydrate used, and D moles of water produced. And of course water has 2 hydrogens in it, so it would be 2D here. And then as another layer, we have the respiratory quotient, which is the amount of carbon dioxide produced divided by the amount of oxygen consumed. So what we did previously is that we solved for glucose utilization and biomass production, where we looked at the amount of carbon in 1 mole of substrate, so 1 mole of glucose, and you'll do something similar on Wednesday. And then we said, okay, we have our carbon, our amount of carbon in 1 mole of substrate. 2/3 of carbon is converted to biomass, the other third is converted to carbon dioxide, and we split it up accordingly. And so that made it fairly easy to calculate, to solve our carbon mass balance and to calculate some coefficients. So we could get the C coefficient according to, so we had 48 grams as our biomass, which was equal to C times 4.4 multiplied by 12. So the 4.4 comes from the biomass multiplied by 12, and that gave us 48 equals 52.8 C, and we could then calculate our C as 0.91 here. And we could calculate E as well, as 24 grams is equal to basically 12 grams per mole of carbon multiplied by E, the coefficient E, and that gave us 2. So E was 2 and C was 0.91, and then we can solve our other balances and calculate our other molar coefficients from there, which we did. So then with all this stuff, having done all these balances and made these coefficients, we can then calculate some yields, or at least some theoretical yields anyway. So we can determine our yield of biomass per substrate as 0.91, and if we want to do molar yields, well, we don't need to go any further. 0.91 is it. But if we want weight per weight yields, we just do 0.91 multiplied by the molecular weight of biomass, so we figured out the molecular weight of this formula, divided by the molecular weight of our substrate, and that gives us 0.461 grams of dry cell weight per gram of substrate utilized. We could do the same, the biomass yield per oxygen consumed, and again 0.91 multiplied by our molecular weight of biomass multiplied by 1.549 times the molecular weight of oxygen to give us 1.677 grams of cell dry weight per gram of oxygen. And if we had experimental data that we wanted to look at, we could compare the yields from our experimental data with the yields that we calculated here. And we could also use those yields in heat balances if we so wanted to. And consider what we talked about today with looking at the yields and the rates of production here. So we had growth and ethanol production for Saccharomyces cerevisiae. And we made our specific rate vector to take into account the rates of growth, the rates of production, ethanol, carbon dioxide, water, the rates of utilization, substrate, oxygen, and nitrogen. And then we can specify the elemental composition of the substrates and products and get a mass balance. Again, the mass balance is set equal to 0. Okay, so given we have our mass balance here, we can put together our elemental composition matrix E, which again shows each column a different component in this mass balance here, and each row is a different element. So we can easily pick out what's what. The biomass is the first column here, followed by ethanol in this case, carbon dioxide, water, the substrate, the oxygen, and then the ammonia finally. And so we could do this for any substrate to product and biomass scenario, and that's part of what the online class is going to be on Wednesday, setting up elemental matrices like this. So we have our elemental matrix, and we put together our R matrix earlier, and we can also change R into a matrix of yield coefficients. And then with that we make a bunch of different mass balances here. So we do the matrix math, we get a bunch of equations, we set these equations all equal to 0, and that gives us a bunch of mass balances for each element. Okay, so what we will do for Wednesday's flipped class, instead of looking at Saccharomyces cerevisiae making ethanol, we're going to look at E. coli making aromatic amino acids. And here are the aromatic amino acids: phenylalanine, tyrosine, and tryptophan. So these amino acids are, as you might remember from homework 1, they're quite expensive to make, but they are very useful in terms of just being amino acids themselves, and for the most part essential amino acids, as well as being important in production and other productions. So here is a pathway looking at the different amino acid biosynthesis branches off of the stoichiometric pathway, which comes off of phosphoenol pyruvate and glycolysis. So we can see phenylalanine here, tyrosine, and tryptophan. And we can see that these pathways are fairly intricate and complex, a lot of genes, a lot of enzymes to make these different aromatic amino acids, which might go a long way to explaining why these amino acids are so expensive in terms of ATP. But again, they're very useful, and they can be precursors to other types of molecules here. So things like melanin, phenol, phenylethanol, enterobactin, and things like that can be produced using these aromatic amino acids as precursors. So they can be used to make useful product, bio-based product chemicals. These aromatic amino acids can. Okay, so the scenario that we will deal with on Wednesday is that we're looking at two strains of E. coli, one that overexpresses these aromatic amino acid biosynthesis pathways and produces a lot of these aromatic amino acids. And we will compare carbon balances from the wild type strain and the overproducing strain. So essentially we'll look at excess amino acids versus no extra amino acids. We'll use the material balances, we'll use black box model, and start to look at this. And of course, like every good flipped classroom, we'll have some assumptions, and I've listed them here, and you can see them on the assignment sheet. The original E. coli strain can convert 2/3 of its growth substrate to biomass, and the E. coli strain that overproduces amino acids can convert 1/2 of its growth substrate to biomass, and the other half is split. A quarter of the entire growth substrate goes to carbon dioxide, and a quarter of the growth substrate goes to these amino acids. The general formula for our product, the aromatic amino acids, I've kind of made a average formula here for aromatic amino acid, which is CH 1.06, O.24, N.13. And again, this is kind of reduced so that we have 1 mole of carbon to keep the carbon balance simpler. The formula for E. coli biomass will be here, as you can see, and the formula for glucose will be reduced also to CH2O. And based on the previous assumption, this formula, the amount of carbon in 1 mole of glucose will therefore be considered to be 1 mole of carbon, or 12 grams. And so again, these are all done to simplify the carbon balance, which will then kind of springboard you into being able to solve the other material balances to answer the questions that we will answer on Wednesday. Okay, so prior to Wednesday, review the mass balance lectures that we went over, the black box lectures, stoichiometry, your yields, rates, matrices, that sort of thing. Look over the papers that I've posted with regards to the flipped classroom here. You don't need to read the papers cover to cover unless you absolutely want to, but it's not required. Just please look them over and kind of get a general idea of what they're trying to say. And then the groups will be posted, so note your groups. And then when Wednesday rolls around, come into class prepared to do the flipped classroom assignment with your assigned group. And as always, I will be strolling around hoping for questions and answering, and hopefully in general providing help. So if you have questions, we can discuss on Wednesday as well. So I will see you on Wednesday, and if you have any questions in the meantime, please don't hesitate to send me an email and get in contact with me. Thank you so much.